Desert noon. The light outside is almost white hot. The thermometer reads 44 degrees Celsius, 111 Fahrenheit. You step through a wooden door into the cool shade. Inside, a quiet rush of air slips past your cheek, as if the house is breathing. The room is 22 degrees. No fans, no motors, no hum of compressors, just silence, stone, and a shaft of sky. For centuries, cities in Persia, present-day Iran, kept people cool in deserts that should have been unlivable. They did it without electricity, without fossil fuels, and often with better comfort in the harshest heat than modern glass towers that guzzle air conditioning all day long. How? With an elegant marriage of underground rivers, tall wind-catching towers, clever geometry, and the oldest refrigerator you've never heard of, the night sky. It sounds impossible, yet we have the blueprints, the ruins still standing, and entire neighborhoods that breathe this silent technology. And here's the paradox. As we rush to air-condition the world, those ancient tricks might save us more power than any new gadget, if we remember how they work. By the end of this hour, you'll know how a 2,000-year-old network of tunnels can beat a modern AC unit at its own game, what the sky has to do with refrigeration, and why a city that treats wind like water might just change the future of climate tech. Stick with me, because the part that sounds like magic, the ice that forms in the desert under the stars, that part is real. Imagine Yazd, central Iran, summer. The land is the color of baked bread. Adobe walls rise high, their tops jagged like waves. Above the roofs, strange towers with slit-like windows face the horizon like sentinels. They're called badgers, wind catchers. They watch the sky, waiting for wind. Morning begins with the soft clatter of a shopkeeper opening a wooden lattice, light filtered through carved screens that paint the floor in shadows. The alleys are narrow and curved, like streams. You hear a whispering sound, not water, but air moving, guided by architecture. We meet an apprentice builder 300 years ago under the Safavid dynasty. He wakes before sunrise. His master is a mechanic, a Kanat engineer. Kanats are underground tunnels that capture water from distant mountains and deliver it to cities with nothing but gravity. The apprentice follows his master past the city walls, out to a plain where a row of small craters punctuate the ground. Each crater is a vertical shaft, a scar of human persistence, leading down to a tunnel that runs for kilometers. The mechanic ties a rope around his waist and descends into the cool darkness. Above ground, heat, glare, desiccating wind. Below, 15 degrees Celsius, damp air, the echo of water coursing over stone. Kanats are veins the city their body, and weighted above ground are the lungs. The wind catchers' chests rising and falling as pressure invisibly changes over their apertures. Persia's central plateau taught its people harsh lessons. Rain is rare. Evaporation is relentless. Groundwater is life, and summer temperatures can cook clay. But here's another lesson the land taught. The desert is also a machine. It has a daily rhythm. Hot days, cold nights. That if you learn, you can store cold like grain. Space is a heat sink. The sky itself can drain warmth from your house. So the builders designed with 3 elements in mind. Wind, to push and pull air through their buildings. Water, hidden in the earth, to cool that air. Mass, thick walls, to store night's cold for the day. Add one more, the night sky, as real a component as any brick. If you live today in a city where the summer heat blares down glass and asphalt, where AC units roar and drip, it's hard to imagine a city actively shaped to be cool. But slab by slab, Yazd and its sisters were precisely that, cities engineered as climate machines. Every courtyard, screen, vault, and lane worked like a part in a device. And at the heart, the wind catcher, an architectural organ designed to harvest the pressure differences swirling over rooftops. This is the challenge our ancestors faced. Make a livable 22 degrees out of a 44-degree day, using only materials you can make by hand and forces you can't see. And in doing so, they discovered something that modern HVAC often forgets. Comfort is not just cold air. It's movement, humidity, radiant temperature, and the story your body tells itself in a room. Stick around. We're going to climb that tower and crawl that tunnel, and you'll see how the two connect in a way that would impress any engineer today. Let's lift the hood on this ancient machine. At first glance, a wind catcher is just a tall tower with slits near the top, but the shape is a carefully tuned aerodynamic instrument. There are types: one-sided towers that face the prevailing wind like a ship's prow, four-sided towers that can catch from any direction, and hybrid towers with internal vanes. Wood or brick partitions that split and guide flow down one shaft and up another. Why tall? Because higher up, wind is faster and less obstructed. Faster wind means lower pressure. Bernoulli's principle says, where air speeds up, its pressure drops. A slit on the windward side sees higher pressure. On the leeward side, lower pressure. That difference can be harnessed. The windward opening pushes air down into the house, and the leeward opening sucks air up and out. In a four-sided wind catcher, no matter which way the wind blows, one face can push and another can pull. The tower becomes a pump with no moving parts. Inside, vanes can do more. They create separate channels, ensuring that the push channel sends fresh air down, while the pull channel extracts warm, stale air up. The vanes increase surface area, slow turbulence, and allow trapped hot air at the ceiling to escape. The height of the tower also unlocks the stack effect. Hot air naturally rises and creates suction. At night, when wind dies, the tower still breathes because warm indoor air wants to climb. But wind is just the first trick. Follow the brick shaft down into the house's heart. There's a room below ground, the sardab, a cool cellar with vaulted ceilings. Here, you hear water. The air from the wind catcher is directed over a small surface of flowing water, sometimes a shallow pool, sometimes a step cascade called a salsabil. The water might be supplied by a cannon running beneath the house. Now your brain wants numbers. How much cooling can a trickle of water provide? This is where an ancient art meets modern psychrometrics, the science of air and water vapor. Dry air can hold only so much moisture. Heat and humidity are linked. In dry climates, adding moisture to air, evaporating water, takes a lot of energy in the form of heat. That energy is absorbed from the air itself, lowering the air's temperature. This is evaporative cooling. Farmers know it when they spray mist on orchards. You know it from sweat. Engineers know it from the psychrometric chart, a map where adding moisture at constant enthalpy slides you along a diagonal path to a lower temperature and higher humidity. In Yazd in midsummer, a typical afternoon might be 38 to 42 degrees Celsius with relative humidity under 15%. The wet bulb temperature, the lowest air can go by evaporation alone, might be around 18 to 20 degrees. That's the absolute theoretical limit for an evaporative cooler. And that's what the Badger Salsabil combo aims at. Push hot, bone-dry air across water in a shaded, slow-moving chamber, and that air will give up heat to evaporate the water, dropping in temperature dramatically. Picture the path. Hot desert air, baked at 40 degrees, is caught by the tower, pressured down a shaft where its speed is controlled. It meets a salsabil, a series of tiny waterfalls on a ribbed surface, maximizing evaporation. The air cools to the low 20s, picks up humidity from near zero to a comfortable 30 to 40%, and spills into the living space. Meanwhile, stale warm air is drawn up an opposing channel and out. This isn't a fan blowing at your face. This is a lung circulating the room. Now let's add the next layer, the earth. Underground is a different climate. Slow, steady, and heavy. The soil at a few meters depth keeps a temperature close to the yearly average. In central Iran, that might be 15 to 20 degrees. Builders leveraged it in two ways. First, by placing the living spaces partially below grade. Semi-basements with high ceilings and vents. They automatically pre-cooled incoming air. Think of the earth as a gigantic heat exchanger. The walls themselves absorb heat by day and release cold from the previous night. Second, they ran air channels, sometimes directly into the cannet tunnels. If you force hot air through a tunnel where cold water flows, you do two things. You cool the air by conduction to the cold surface and by evaporation of the water. The air that emerges can be astonishingly cool, and because it has traveled through a long, shaded tunnel, it's often calm and not dusty. In some houses, the wind catcher does exactly this. Instead of sending air straight to the rooms, it sends it down to kiss the can of water first. If the wind slows, the stack effect still pulls the air over the water and up into the rooms. In reverse, on humid days when you don't want extra moisture, the tower can be configured to suck hot air out without pushing it across water. Just ventilating, using the dryness of the underground to strip heat without adding humidity. Already, this system is modular. You can run it in different modes depending on weather. Evaporative mode when air is dry and hot. Ventilation mode at night to flush heat and recharge the thermal mass. And stack only mode at dawn when the outside is cooler than inside. Now, add the final layer, radiation to the night sky. We have a sense that at night, deserts get cold. But it's not just lack of sun. Even in daytime, surfaces radiate heat as infrared light into the sky. The atmosphere isn't perfectly opaque to this radiation. There's a window in the infrared spectrum, roughly 8 to 13 micrometers, where heat can escape to space. Space is effectively a 3 Kelvin heat sink, unimaginably cold. On clear, dry nights, a surface that sees the sky can dump heat there faster than it receives it from the air. Builders in Persia knew this without the physics. They used it to make ice. The structure is called a yakshal, literally ice pit. Imagine a cone of mud brick as tall as a house, with walls over 2 meters thick. Inside is a deep pit. Outside, high walls cast shade over a long, shallow pool. At night in winter, water is poured into the pool. Even if the air is just above freezing, the water's surface radiates heat to the sky, dropping below the ambient temperature and forming ice. By morning, men break the thin sheet and carry blocks into the yakshal, layering them with straw. Through spring and summer, the thick, chalk-coated walls keep the interior cold with insulation and evaporation of water in the porous clay. When the town needs cold, someone descends into the pit and hauls up a block. Radiative cooling also works in summer at night. In courtyards, by morning, stone basins can be cooler than the air because they've been quietly bleeding heat to the sky all night. Traditional houses use that to their advantage. They ventilate at night, flushing hot air out while thermal mass. Thick walls, floors, and the ground. Sucks in the chill. Doors stay closed by day to trap it. If you pay attention here, you see the outlines of a complete system with no moving parts, daily charging and discharging. The wind and the sky do the work. Water multiplies the effect. You might be thinking, but air conditioning isn't just about temperature. It's about comfort. Doesn't humidity matter? Yes. Evaporative cooling adds moisture, which can feel muggy. But in places like Yazd, baseline humidity is so low that bringing it up to 30 to 40% actually feels better. Your skin stops cracking. Your sweat becomes more effective. In the Gulf Coast, where humidity can be 70 to 90%, Persian merchants adapted the Badger differently. They used the wind catcher mainly for ventilation, with the cold coming from thick walls, shading, and night flushing. In Dubai's Bastakia district, the bargeel, derived from the Persian badger, gives relief even when it can't drop the air all the way to the wet bulb. Let's put rough numbers on the performance with an example. Take a Yazd afternoon, 41 degrees Celsius dry bulb, 10% relative humidity. Wet bulb is around 19 degrees Celsius. A well-designed wind catcher with a salsa bill can bring air down into the low 20s, say 22 to 24 degrees Celsius, and raise humidity to 30 to 40%. The incoming volumetric flow might be hundreds of cubic meters per hour, depending on tower height and wind. Because of the stack effect, the system doesn't need continuous wind. Night flushing might bring room walls down to 15 to 20 degrees Celsius. By noon, the walls slowly warm, but the air you breathe is continually replaced with cooled air. Subjective comfort? High. Energy input? Just a bit of human work to maintain channels and pools and the water itself. Delivered by gravity. Compare that with a modern AC, which could smash the air to 18 degrees Celsius no matter the weather, but at a cost. Electricity to run compressors and pumps, plus the environmental cost of refrigerants and heat rejection that bakes the street outside. AC handles humidity, too, but again at a huge energy cost. Does this mean Badgers are better than AC? Depends on what you mean by better. If better means life cycle energy, carbon, and resilience. Staying cool in a blackout. Many Badger houses win outright in their climate. They deliver high comfort in hot, dry weather with negligible energy. If better means precise control in all climates at all times, AC wins. But we're getting ahead of ourselves. The story isn't a competition, it's a synthesis. Before we leave the engineering lab, look at the map of Persia and beyond. Iran's Central Plateau incubated the Badger, but similar ideas arose wherever people faced heat with little technology. In Iraq in the Gulf, wind towers and serdabs, subterranean rooms, persisted into the 20th century. In Egypt, the Malkaf is a similar wind scoop used in medieval Cairo. In Pakistan and Rajasthan, there are jollies, car screens, that diffuse light and move air. The principles rhyme. Shape the wind, cool with water, store the night. Now let's step from the lab back into the street and trace how this ancient cooling system ripples into modern engineering, architecture, and even the design of data centers. Stand on a rooftop in Yazd, barefoot on warm brick. Push your hand into the mouth of a wind catcher and feel the pressure. It's not a gale, it's a persuasion. Now think of how modern HVAC usually works. A sealed box, windows shut, a machine that shoves cold, dry air until a thermostat says stop. It's gloriously brute force. It also consumes, on hot days, as much electricity as almost any other appliance. In some Gulf countries, air conditioning consumes more than half of all electricity in summer. Worldwide, AC is one of the fastest growing uses of energy, and the very waste heat from AC units is a major contributor to urban heat islands. The ancients had no grid to lean on, so they leaned on physics. That's the first legacy. But the really interesting legacy is conceptual. They treated cities as climate devices, not just buildings as isolated objects. Let's connect the dots to modern tech. 1. Evaporative cooling. Ancient edition versus modern swamp coolers. Those boxy units you see on roofs in Phoenix and inland Australia. Swamp coolers are fans that blow air across wet pads. They're efficient in dry climates and cheap to run, dropping indoor temperatures by 10 to 15 degrees Celsius with much less electricity than compressor-based AC. The Badger Plus Salsa Bill does the same trick, but replaces the fan with wind and stack effect. That means zero electricity when designed well. The two share constraints. They work best when the outside air has low humidity. Yet modern engineers keep improving evaporative systems with strategies right out of the Badger playbook. Multi-stage evaporative cooling, indirect first. Cool the air with a humidified heat exchanger so you don't add moisture to the room. Then direct evaporative, careful control of airflow, and the use of tall shafts to drive buoyancy. Some modern buildings now add elegant evaporative features at the architectural scale. Perforated ceramic panels that weep water, central atria with waterfalls whose surfaces are tuned to maximize evaporation without drenching anyone, roof vents that act as controllable badgers. 2. Night flushing and thermal mass. Green building standards. From LEED to passive house. Now prize night ventilation and heavy materials. The idea is almost a translation of Yazd. At night, open the vents, let cool air rush through, strip heat stored in the day, and then close up during peak heat while allowing gentle air movement. Massive walls and floors are not just structural. They are batteries that store cold. There are even phase-change materials embedded in drywall that mimic the way a thick adobe wall soaks up heat. Some modern office buildings in London and Frankfurt use automatic windows that open at night. Their concrete cores charge to below 20 degrees Celsius, enabling comfortable midday temperatures with minimal mechanical cooling. Data centers, repositories of the world's information and heat, use free cooling at night where climates allow, pulling in outside air, filtering it, and flushing heat without chiller use. In cooler places like Luleå, Sweden, Facebook servers run on wind-cooled air most of the year. In arid climates, data centers add adiabatic cooling, spraying a fine mist upstream of intakes to drop the temperature before it hits the servers. That's a high-tech salsa bill. 3. Ground coupling and earth tubes. Modern earth tubes, long-buried pipes that draw incoming air through the ground. Pre-cool or preheat ventilation air using the soil as a heat exchanger. In the best designs, air enters a building already close to 16 to 20 degrees Celsius in summer. It's the can it trick without the water. In the worst designs, they collect condensation and mold because designers forgot the ancients' wisdom. Use lime plasters to resist microbes, slope drains, and keep velocities low and surfaces smooth. Those details, mundane and life-saving, were part of McCanney's craft. They checked slopes by eye, kept gradients slight, 1 in 1,000 to 1 in 1,500, to keep water moving but not eroding, and lined tunnels with stone and plaster to resist collapse. The Earth's coolness wasn't just a concept. It was a discipline. 4. Radiative cooling to the sky, rediscovered with material science. In the last decade, engineers have developed metamaterials, engineered surfaces that reflect sunlight and radiate heat in the 8 to 13 M band efficiently even under full sun. Roof coatings that look white but behave like miniature radiators can sit 5 to 10 degrees Celsius below ambient at noon in some conditions. This is the Yakshal principle turbocharged. One Stanford group even ran a prototype that cooled water below ambient in daylight. That's an open invitation to revive night sky cooling in modern cities, not just at night, but all day, for things like pre-cooling return water in cooling loops or taking edge off peak heat. Pair radiative cooling with thermal mass and smart shading, and you have an ancient modern hybrid that pushes buildings into comfort with almost no electricity in dry climates. Put a radiative cooler at the top of a ventilation tower, and the whole tower becomes a badger that not only uses wind and stack effect, but actively rejects heat to the cosmos. 5. District cooling and deep water intakes. When you think of a cannet, think of a passive distribution network for a thermal resource. It's water in Iran. In Toronto, it's cold. Toronto's Deep Lake Water Cooling Project pulls 4 degrees Celsius water from Lake Ontario, runs it through the city's glass towers to absorb heat, and then returns it. Some Middle Eastern cities now use seawater-cooled district cooling, where a central plant uses the ocean as an immense heat sink and sends chilled water to whole neighborhoods. In Oman and the UAE, planners are mixing district cooling with wind towers in new cultural sites. Is this cheating? It's modern, but it's the same conceptual move as the cannet. Connect your building to a steady, passive resource and share it. A single chiller is like a badger. A district plant is like a network of badgers feeding and breathing together. The energy and emissions savings are huge. 6. Modern wind catchers. Tested and revived. In the last 20 years, architects in Iran, the UAE, and as far as Arizona have revived and reimagined badgers. Masdar City in Abu Dhabi built a central wind tower that uses sensors to rotate vanes to face the wind and misting nozzles to cool the shaft. Traditional neighborhoods in Yazd and Kashan have restored wind catchers whose performance rivals modern HVAC in hot, dry summers, often keeping indoor air at 26 degrees Celsius or lower in the hottest afternoons. Educational buildings in the UK have experimented with wind towers with controllable dampers, combining natural ventilation with mechanical assist on still days. There are cautions. Dust, ubiquitous in the regions where badgers are at home, can clog dampers and salsa bills, and the fine powder can ruin indoor air if not filtered. Designers now add simple filter screens at tower mouths, something some historic towers also had in the form of woven reed screens. Water consumption matters. In cities where groundwater is under stress, evaporative cooling needs careful accounting. But compared to a standard AC's lifetime water footprint, remember, power plants consume water too. Well-designed evaporative systems can be competitive or better especially if they draw on non-potable sources or condensate recovery. 7. Adaptive comfort and human expectation. There's a subtlety ancient builders understood intuitively. Comfort is contextual and adaptive. People in a naturally ventilated house are comfortable at warmer temperatures than people in sealed, air-conditioned spaces. If the air is moving gently, if humidity is reasonable, and if radiant temperatures from surrounding surfaces are cool. Thanks to night flushing, then 26 or even 28 degrees Celsius can feel good. Modern comfort models, like Oshry's adaptive comfort standard, now reflect this. That means a Badger house can be better, not because it hits a thermostat number, but because its total comfort package. Air movement, humidity, radiant balance, psychological enjoyment of a breeze. Beats an AC chilled, stuffy room that dehydrates your skin. 8. Resilience. Think of a heat wave and a blackout. In 2003, a heat wave in Europe killed tens of thousands. In 2021, parts of the Pacific Northwest sweltered with temperatures never seen before. Modern cities depend heavily on the grid to be livable. Passive systems that reduce peak demand and keep buildings tolerable without power are becoming one of the most important features a city can have. A Badger basement house doesn't fail when the power does. It rides through. Coupled with rooftop radiative coolers and even a small solar-powered fan assist, you have a cooling system that can function off-grid indefinitely in hot, dry climates. 9. Culture encoded in engineering. Ya's urban plan is a machine for human rhythms. Narrow lanes. Shade, high walls. Shade, courtyard houses. Microclimates, wine towers. Ventilation, water channels. Cool basements, night activities. Use of daily cycles. Modern planners chase walkability and green infrastructure. Ancient Persians built thermal infrastructure, which was green by necessity. You can almost see it as a feedback loop. Technology shapes behavior, behavior optimizes technology. Of course, not all was utopia. Cannon construction was brutally hard and dangerous. Mechanics spent their lives underground. Maintenance was constant. Cities outgrew their water budgets. As diesel pumps proliferated, water tables dropped, many cannons ran dry, and wind catchers were bricked up as people turned to electric AC and minimal maintenance appliances. As the 20th century progressed, thick bricks became thin concrete and glass, easy to throw up, hard to cool without machines. The old knowledge faded, yet the physics never changed. And in a warming world, with millions of people in hot, dry climates, the old city's lungs deserve a second life. If you've enjoyed tracing the line from Badger to data center, hold on. The most mind-bending part is coming. It's the piece that unites wind, water, and the night sky into a single principle. A principle that points to a design revolution hiding in plain sight. If you peel a modern air conditioner into its fundamental parts, you get a loop. A compressor squeezes refrigerant, raising its temperature. A condenser coil dumps that heat to the outside air. An expansion valve lets the refrigerant evaporate inside, sucking heat from your room. And a fan moves air across these coils. It's a heat pump, moving heat from inside to outside. It works brilliantly, but it has a problem. On a 44-degree day, the outside is hot. You're pushing against the ceiling of the climate you're trapped in. Your condenser has to be bigger, your compressor louder, your electricity bill higher. The ancient system has no compressor, but it has a condenser, hidden in plain sight. It's the sky. The wind catcher handles the movement of air like the fan. The salsa bill and the cannon act like the evaporator, using water's latent heat to absorb thermal energy from the air. Where does that heat go? Into the water and into the thermal mass. At night, the system flips. The heat that built up in walls and water radiates into a black dome a few degrees above absolute zero. It leaks away through the atmospheric window. The city's condenser is the universe. This is the aha moment. They arranged a loop with wind pressure as the pump, water's phase change as the refrigerant side, mass as the buffer, and the night sky as the dump. It's a heat pump made of climate. You can almost draw it. Day, hot, dry air, wind catcher, salsa bill, cooled air to rooms. Water warms and evaporates. walls absorb. Exhaust heat rises and leaves via wind towers, leeward channels, and roof vents. Night. Doors and vents open, cool night air flushes rooms. Walls release stored heat. Pools and roofs radiate to the sky. If winter, Yakshul makes ice. The city dissipates the day's thermal load to space. It's elegantly self-similar, and it exploits the very asymmetries that make deserts harsh. Large day-night swings, clear skies, sparse humidity. The system works best where modern AC works worst, where the outside is hellish, but the sky is perfectly aligned to carry heat away if you can expose it. We can quantify it, at least heuristically. A surface under a clear desert night can radiate on the order of 100 to 150 watts per square meter of net heat loss to the sky. Multiply by roof area, pools, and walls, and you're looking at kilowatts of cooling power every night. Free, passive, and scalable. During the day, radiative heat loss is cut by the sun, but with new radiative metamaterials that reflect almost all sunlight while emitting in the thermal infrared, we can regain some of that midday advantage. Now imagine a wind tower capped with such a radiator. Its interior lined with ceramic pads fed by gray water trickles. Its base built over a low, shallow basin. The air inside flows downward, cooled radiatively and evaporatively, and a separate shaft draws heat up. From the street, it looks like a modern badger with shimmering white skin. Inside, the air is 8 to 15 degrees Celsius cooler than outside most of the year. Add to that an urban rule. Do not fight the climate with a single building. Plan neighborhoods to create pressure differentials. Alleys aligned to prevailing winds, planted courtyards that exhale at night, public cisterns that double as cooling basins. At peak heat, your goal is to lower the city's nocturnal heat content. The atmosphere becomes the infinite sink. The city just needs to expose itself to it. Every restored thick wall, every shade-giving arcade, every roof that radiates to the sky lowers the next day's baseline. This is where better than modern AC earns its meaning. If you measure performance by energy and resilience relative to comfort, these systems are astonishingly good. They're not universal. In humid climates, evaporative cooling adds stickiness. In polluted cities, open windows bring in smog. There are reasons to keep your glass sealed. But the core twist is this. The ancients found a heat sink bigger and colder than any chiller's condenser. And when the grid fails, the sky keeps working. There's one more human twist. The Mechani and the Badger Builder were not isolated craftsmen. They were embedded in guilds, regulated by community norms that allocated water and rights. A cannet is a social contract. It crosses villages, farms, and city blocks. It must be maintained, its flow monitored, its branches apportioned. The badger is the household's claim on climate, but the cannet is the community's artery. When diesel pumps made it easy to drill personal wells, the contract frayed. Groundwater fell. Cannets went dry. Wind catchers, dependent on air and water, lost their second half. There's a lesson here the modern world is relearning under duress. Climate comfort is a shared system. Your AC unit dumps heat to the street. Enough of them, and the street becomes an oven. Your evaporative cooler needs water. Your neighbor's well is connected to yours. In the ancient city, harmony was enforced by necessity. In the modern one, it will have to be enforced by policy, and by design that makes the good path the easy one. If you're still thinking about that apprentice we left at the cannet shaft, imagine his first night back in the city after his descent into the earth. He lies on a rooftop under the stars. He feels the desert's breath turning cool. He knows that breath will be inside his house by noon tomorrow, and that somewhere in the darkness below, a tunnel built by his grandfather is moving the desert's one river toward a wind tower built by his uncle. The house itself balances competing flows. He spent his life tuning it. That's more engineering than romance. But it sounds like a future I want to live in. One where the city and its climate are not at war. We started with a door opening from a 44-degree street into a 22-degree room with no electricity. We followed the breeze up a tower and down into a tunnel. And we watched ice form under stars. The ancient Persian cooling system worked because it wasn't a gadget, but a grammar. A few simple words: wind, water, mass, sky, made sentences that could be spoken at the scale of a house, a block, a city. Many modern buildings, by contrast, are single nouns, sealed and self-contained. They are comfortable until the power goes out or the climate shifts beyond their design. I don't want a false choice. I want the ancient grammar taught to the modern building. Imagine neighborhoods in Phoenix, Tehran, Jaipur, and Marrakesh where wind towers rise above trees, where night sky coolers line the rooftops, where courtyards breathe and streets curve with shade, where modest mechanical systems fill the gaps instead of carrying the entire burden. Imagine a data center whose condenser is partly space. Imagine a school that stays open in a blackout because it was designed to be alive to wind. If you enjoyed this dive, here are 2 threads you might want to pull next. The forgotten refrigerator: how Persians built yakshuls that made and stored ice through blazing summers, and how radiative cooling materials might bring them back above ground. The underground internet of water: the world-spanning Canet and its cousins, the social tech that kept deserts alive, and what happens when pumps break the pact. Let me leave you with a question. Where you live, what's your sky worth? Is it just a roof to keep off rain, or is it an engine? The people of Yaz didn't just look at the stars. They put them to work.